So last time we were discussing the postulates and had almost finished the basic discussion. And the last postulate which we were talking about was the collapse postulate. And what it said was that if you are in a state psi, in any state psi, well, I had written it, so I'm not going to write it again. Just let me pictorially draw it that you are in state psi. You make a measurement which gives you measurement of an observable O. And as per our one of the previous postulates, it gives you one of the eigenvalues of O, W1, let's say Wi. Then immediately after the measurement, the state will collapse to the corresponding eigenstate of O hat. Now, afterwards, so this is what happens immediately afterwards. And after this, the state will continue to evolve according to the Hamiltonian evolution. But this is now acting on, so suppose if it happened at t equals 0. So at a later time, your state will be given by the usual evolution with whatever the Hamiltonian is for the system. Did we write it with a minus or a plus? I think, let me see. Yeah, with a minus. So this is the evolution operator. Before, it was evolving through this evolution operator. And after the collapse, it again evolves through evolution operator. But in between, when you make a measurement, something drastic happens. It forgets whatever evolution it was doing, and it collapses to the corresponding eigenstate. Now, an issue which can arise over here is that you have this Wi. I think we had discussed it before as well, but in relation to collapse, let me make a statement again. If Wi is degenerate, that means more than one linearly independent vectors have the eigenvalue Wi. Then we know that there will be a eigenspace. So let's suppose if there are two of these, two linearly independent. So this whole eigenspace, let's call it Wi eigenspace. All vectors of this form, they all have eigenvalue Wi. Now, we had said that if we compute the probability, if you are in state psi, then what is the probability of getting the eigenvalue Wi in case when this eigenvalue is degenerate, let's say twofold degenerate. So this would be the probability coming from this falling into one of the choice. So you have this two-dimensional space. You can pick any orthogonal set, orthogonal basis in this. So then when you will get the eigenvalue Wi, you think of it that it could be coming from one orthogonal choice, one vector from the orthogonal choice or the other. So you have this probability plus this probability, because it could be coming from either this one or that one. So the both probabilities add. And this thing,
सर ये 1 होगा इसका आंसर एड ऑफ प्रोबेबिलिटी.
1 क्यों होगा? You are in some state psi. Usually the probability to get eigenvalue Wi is just this. Mod square, right? That's the postulate.
Yes.
So what I'm saying is when Wi has two possibilities.
सर
Hmm.
सर मेरा ख्याल है जो रजीन पूछ रहा था वो मेरे दिमाग में भी आया कि इट्स द समेशन ऑफ होल प्रोबेबिलिटी या फिर मतलब तो वो 1 होती थी तो इस वजह से उसने
Not
मेरा ख्याल है
summation of
पूछा है
all
तो
probabilities.
नहीं है ये सिर्फ एक स्टेट में होने की है तो
एक
इट
स्टेट में
कैन बी
होने की
लेस.
नहीं है. It's not being in one state. आपके पास जो, let me draw these think of them as orthogonal, although they don't look like because I cannot draw multidimensional spaces. You have all these eigenvectors corresponding to different eigenvalues of your, आपके पास कोई ऑपरेटर है O hat जिसकी आप ऑब्जर्वेशन कर रहे हैं. इस ऑब्जर्वेशन के लिए आपके पास पॉसिबिलिटीज हैं W1, W2, जो भी इसके आइगन वैल्यूज हैं वो आपकी ऑब्जर्वेशन में आ सकती हैं. Corresponding to each eigenvalue, you know that you can decompose any state psi as a linear combination in its eigenbasis of O. And our postulate says that if this is normalized, if psi is 1, then probability of any one of them occurring in the measurement, let's say W2, is just the coefficient of W2 mod square, which is same as, because they are orthogonal, mod square, because when I'll hit this with W2, they will all be 0 except for this guy. Now the issue is that it can happen, let's say ith one of them, ith eigenvalue is twofold degenerate. So ith eigenvalue can come if you project to this or if you project to that. So when you get Wi in your measurement, you don't know if it's coming from this or that. So the probability of Wi coming is simply probability of this happening or probability of this happening. And you know well that by the rules of probability, when you have an or statement, this happens or that happens, then the probabilities just add. So therefore, probability of Wi would be this coefficient mod square plus the probability that it could have come from the other. So you should think of it that your vector is somewhere, and when you make a measurement, it drops to one of the bases. It collapses to one of the basis vectors, or you can say it projects to the one of the basis vectors, and according to a certain probability. But when you have a degenerate eigenvalue, then you don't know that if it collapses to this Wi1 or Wi2. So it could have collapsed to either one of them to give you Wi. So probability will simply add that it could collapse to 1 or to 2. So this would be the probability, which is exactly what I have written over there, because this coefficient is this number. Right? Now, यही जो चीज़ है, इसको I can write this way, because this is the side, this number start with this number itself, and you make the star by flipping the order. Similarly, maybe let me go down. इस तरह से लिखने दें. So it's the same thing, and this is the same thing. But over here, now I can write it this way. This looks like an operator. Plus this is called the projector to Wi eigenspace. Because what it does, it exactly projects. If you take a vector psi, you apply this projector, what is it doing? It's picking up its components along two basis vectors of the subspace, and resolving them along them and multiplying with the basis vectors. So these are literally the components of psi along these two basis vectors. So this is simply the projection of psi into your required eigenspace. So what it's saying is that the probability of Wi is simply the projection sandwiched between your state. But this same formula you can write for if you have a non-degenerate eigenvalue. In that case, your eigenspace is just one-dimensional. So your projection along that eigenspace is just simply, let's say, if this is Wj, where Wj is non-degenerate. This is the projection operator for the one-dimensional space. And if I do this, that is the probability, because this is just simply, which is mod square. So if you have degeneracy, just make the projection operator or just add the probabilities of this projecting to one of those, any one of the basis vectors in the eigenspace. So this also means for the collapse, if you get the eigenvalue Wi, which is degenerate, the state vector collapses to one of the vectors in the eigenspace. Which one? We don't know. It could be Wi1 or Wi2 or any linear combination. Any one of them can give you the desired eigenvalue outcome. So which one is it? We don't know. So the best you can say that you have collapsed to the eigenspace. Although you are collapsing to only one vector, but that vector, the best you can say is that the vector belongs to the corresponding eigenspace. And if it's multi-dimensional, then all you know is that it's one of the vectors, but you can't say which one. And you have to realize, like, if I'm saying it's a vector in this two-dimensional vector space, it's up to the multiplication. So suppose you collapse to this vector. I can multiply it with any face. That is all understood. I identify all of them with the state which I get. I count them as one vector. So I'm talking about ways, picking a way in this subspace. Now let me make some general comments about the postulates. So one of them I can say right away is the following. So I can have an operator. I can have an observable whose corresponding operator has a continuous eigenvalue spectrum. So in that case, nothing changes much. So let me just start with explain this with an example. So for example, we said that for position, the corresponding operator is x hat, and we know this has a continuous eigenvalue spectrum because all of these are eigenvectors. So in this case, if I ask about the probability, if I'm in a state psi, what is the probability of getting a particular position x? So again, you expand it, but this time when you expand it, you have to expand like this. F of x, instead of f of x, I'm writing it as psi of x, which is just a function of x. We know I can expand any vector like this using this function. So what would be the probability? So these are now like components. But now I cannot talk about the probability of finding it at a point. I should be talking about the probability density. So this gives me these components mod square, just like in that case I had in the discrete case I had AI mod square. So these are the same. These are the components, and I take their mod square, and this gives me the probability, but not really probability. This is the probability density. at point x. That means that probability of finding the position x, position between x and x plus dx is this. So if I am given a state psi and I'm asked that what is the probability if I make a measurement for this particle, this state is describing a particle, what is the probability that I'll find the particle if I make a measurement for position between, let's say, x1 and x2. I'm considering one-dimensional problem between x1 and x2. What is the probability? So it would be just sum of these probabilities between x1 and x2. And where I find the psi of x by through this. These are the components of the vector along the position axis, along the position basis. These components, which are a function, this is a function of x, a continuous variable, these are called, this is just a given a name for historical reasons, this is called wave function. It should be more accurately called, well, yeah, sometimes people call it, if you want to call it, give it a complete name, wave function in the position basis. But it is essentially just the components of your vector along the position basis vectors. And so then this is sometimes called, again for historical reasons, Bourne's rule, which we have implemented in a more general way in our postulates. So it's just an application of the postulates that which I have just written, that wave function mod square gives you the probability of the particle being found around a position x. Similarly, you can, I have another example. So this will work for any operator which has a continuous eigenvalue spectrum. You will do exactly the same things. For example, this we wrote last time, that this is also part of our postulate. This is the operator for momentum. So that means if I had these kets, which were the eigenvectors of the k hat, and remember k hat in position basis look like d by dx. So k hat, so p hat, these vectors are then eigenvectors of p hat as well, with eigenvalue k. So these I can identify. This K is also can be labeled to P, where P is H bar K. So now this P hat is a Hermitian operator, same as K hat, because I have just scaled this operator multiplied with a constant. This is called, by the way, again, this constant comes in because of just there's a scale in quantum mechanics, and our units are such that this scale is not one. It has a certain value. This is called Planck's constant. But this K hat was Hermitian. We had made sure that this X as Hermitian because we kept only these vectors, these K vectors in our Hilbert space, which look like this and not these. So if you collect only these, we know that they form a basis for the Hilbert space. So similarly, these guys are also the eigenvectors of P hat, and P hat also is also Hermitian. And we can expand any psi as using the eigenvalues and eigenvectors, because this would be identity. So this thing would be you can say psi P hat, and the probabilities probability of finding momentum between P and P plus dP should be proportional to psi hat P star psi hat P dP. I've written proportionality because you have to normalize them properly, and we already know what the normalization we had chosen. So instead of P label, I can use the K label, and we had chosen that psi K was e to the iota kx. Now remind me, did I put this thing over here or did I include it in the definition of expansion? We have to use what we need to do is use this formula. So over here, I can do this. Because when I do this, what will happen? Then this would be iota k wait. This is psi of, let's call it psi of k tilde, just to differentiate that these are the components of psi in the k basis. And I can find these by doing this. xk. And this one we had called e to the I k x. And if I want to keep the secular, by secular I mean I include, when I do a Fourier transform, this is, was this, we chose it this way, right? And yeah, so I want to include one over here so that this thing would be by inverse Fourier transform e minus iota kx. So that means I can just use this formula and choose this normalization. So what does this give me? Kk dash. I can include now I'll have a 1 over 2 pi coming from here. 1 over under 2 pi coming from here will give me a 1 over 2 pi iota k minus k dash x, and this is equal to the delta function. So they are normalized. These k hat vectors are normalized to a delta function, and so are the and I can label them obviously with a p hat as well, p with a p as well, with the understanding that p is equal to h bar k. Now, so that what does this mean? That means if I have this vector, I expand it in these basis vectors. I have just seen from here that probability of k being between k and k plus delta k, which is same as probability of momentum being h bar k and h bar k plus delta k. So some probability for momentum is just psi k star psi k dk where what is psi k? We just found out that psi, sorry, this I should write with a tilde. We just found out that the psi tilde k is the Fourier transform with this 1 over under 2 pi included, because that makes it orthogonal and normalized to delta function. So that means if where psi tilde k is the Fourier transform of the position space wave function, and you can call this momentum space wave function, and they are related by Fourier transformation to each other. Now, given any this is also a comment. So this was comment 1 probably. Was it? Yeah. So let me write it. For any observable, this is the statement of comment 1. For any observable with a continuous eigenvalue spectrum, psi would be, let's say the eigenvalues are taking some continuous values where E is a continuous parameter. You can still expand like this. The probability of getting value between E and E plus dE around a value E is mod square dE, and psi E is called the, let's say, E space, whatever the observable is, let's say observable E space wave function. Second comment is that, so suppose, so what it means, whatever we have said, that even if we know the state psi completely, and if I make a measurement, then in general, I'm making a measurement of an operator, of an observable with the corresponding operator, let's say omega hat, and it has these possible eigenvalues. In general, even if I know the state completely, I cannot predict which one of them will come out. I can only talk about the probabilities. So for each state psi, there will be a probability distribution for the outcomes of this measurement. So what state psi does for you, it defines for you a probability distribution for each observable. For each observable, it gives you a different kind of probability distribution, but all those probability distributions are contained in this psi, in this state psi. So whatever that probability distribution would be, I can quantify as usual. Well, this is just a comment, not something very deep, but it is like commonly used nomenclature, so we should mention it. That for the probability distribution, you can describe it. One way to quantify it is to define what is its central value, what is the mean value. Mean value of the probability distribution. For the observable omega in the state psi. So depends on both which observable you're talking about and in which state. So what would it be? By definition, this is just all possible, you take all possible outcomes and multiply them by their probabilities and sum. That's the average. Mean value, or you can say average of omega hat. And by the laws of probabilities, what does this average, how would this average be computed in an experimental setup? When you make a measurement, this average doesn't come up in your measurement. So what would this average be? So suppose you have a large number of what we call an ensemble. If we have an ensemble, that means you have a large number of systems, identical systems, each in same state psi. So somehow you know that all of them are in same state psi. We haven't like done an example, a physical example of finding out how to make sure that a certain system is in the same state psi. But apart from experimental setups, that how we actually do it, we are just discussing the theory. If we know that all of them are in same state psi, and we start making measurement, every time we will get a different answer, and we collect the frequency, and those frequencies define for us a probability distribution, and that is the average. We collect all those outcomes and make an average of those outcomes. That's this. And by definition of the average is defined this way. But in our case, this is just psi mod square, right? Because that's the probability. So this I can write as but this right now, if you notice that I have a sandwich of a cat and bra of omega I and sum over I. So can I make it an identity? Is it an identity operator? This is my question to you. Is this an identity operator? So will someone answer? Razeen, do you have an answer?
No, sir.
Why not? I mean, you can make a comment. Remember this thing, for any eigenvectors, if I take all the eigenvectors as I am doing over here, is sum over all, this is identity. So is this an identity? Samreen, what's your opinion?
Yes, sir, seem to be.
It's
Yes,
not.
sir, luck to be.
It's not. It's not because I have these numbers. I'm not just adding these. I'm weighing them with some WI. So it's not identity. Because for identity, for this to happen, has to be 1 over here. Right? Because why would it be identity? Because it resolves any vector into its component, and then it gives it the vector along that axis. But if I multiply each one of them, scale each one of them with some number, then I'm disturbing the components. So when I'm acting on psi with this alpha I, I'm not keeping the components of psi. I'm scaling those components along each axis in different ways. So this is not an identity. If it were an identity, this would mean nothing. Nothing will happen over here. So this is not identity. However, I can write it this way. This is an omega I eigenvalue. I can get this eigenvalue by acting with this operator, because these are the eigenvectors of this operator, and these are the corresponding eigenvalues. The same equation I can write like this. Now there are no omega i's. Now this thing summed. There is no I, no index, summing index anywhere else. So this is an identity now. sum is gone. So this is the average value. So to compute the average value, all you have to do is take the operator and sandwich it between the state. In practical computations, let me just give another comment. So this would be comment 3. In a basis, say position basis, this will look like this. ये average value है. So I can put in, so suppose I want to find average value of this operator. So I can insert two identities, dx and dx dash. I will have psi star of x from here because it's flipped. Then I have the matrix elements. Typically, these involve some kind of a delta function. So one of the integrals will drop. So for example, if I'm doing average value of x, so this thing for x, this thing, we know it gives us x times, so this would be equal to dx psi star of, this was, one of them was, yeah, this was x dash, psi star of x, x psi of x. Which makes perfect sense because psi star x psi x dx is the probability of being around x. So if I multiply it with the x and sum over all those, then I'm computing an average, which is this average. Similarly, if I compute the average for p in the x basis, it would be psi star of x, psi of x dash, and the matrix elements of p between x and x dash. And those we had computed is just the matrix elements of k multiplied with a h bar. These were the elements. So when I'll do the integral, I'll have so in other words, you are just doing this. Make the integral, put the wave function on one side, and put the expression for the operator in that basis. And I know that p hat in the x basis, p action of p hat, it changes the components of psi x to these components. So put that expression in here in x basis and sandwich it between psi star and psi. This will be the average. Similarly, one more thing you can do about quantify the probability distribution is compute the standard deviation. standard deviation or variance, whatever you want to call it. But the main idea is that you take the each eigenvalue you get and see how far away it is from the mean, from the average. So you have these eigenvalues here. You have a certain mean and they're distributed. So you want to get an idea how far they are spread. So you take each eigenvalue and compute its difference from the mean, which is I'm doing over here, and compute that on average where they are. So you multiply it with the corresponding probability of this eigenvalue and do this average. But when I do this, I'm going to the right and going to the left. If I'm on the right, I get a positive difference. I'm on the left, I get a negative difference. So they have a tendency to cancel it out. And actually, if you have a completely symmetric distribution, this would be 0. You don't want it. You want to get a idea that how broad the distribution is. So that's why you square it and call this the variance or standard deviation square, which I am writing like this. In quantum mechanics, the tradition is to call this thing uncertainty. Why uncertainty? Well, literally, this is the average, this is the central point of the distribution. But before making a measurement, you don't know what will come up. And it's quite contrary to what happens in classical mechanics. In classical mechanics, when you have complete information, you can make concrete predictions that where the particle will be. Or if you are talking about right now, you know where the particle is. So you know, so you say that you don't have any uncertainty. You can say things with certainty, that what is the position. In quantum mechanics, even if you know everything about the system, you don't know what will turn up in your experiment. So you say that there's an uncertainty, and one quantification of it is the standard deviation. So this is called the uncertainty. In observable omega, in state psi, depends on which state you are. So this would just be, I have to put the probability here, and the probability is simply mod square. And if you do 2 lines of algebra, well, maybe I should do it. So I can open this up. I get omega I square plus omega square. Remember, this is a number because this is the average value. These are also numbers. These are the eigenvalues. And then I have minus 2 omega I, and this is multiplied by this probability. So it's the same logic as before, that this guy I can write like this. I'm bringing this in, multiplying with every one of them. Now again, this is not an identity because there's a wi square being multiplied. This is not an identity. only this guy is an identity because there's no summation apart from these two guys. So they can be replaced with an identity. But what I can do is the following. So this first guy, I can get this wi square by multiplying, by acting with an with the operator. So this is same as this operator, omega square, acting on these guys, right? And this is same as, I can, if I want, I can write it as an identity operator. Acting on psi. Well, at this step, let me keep writing this. Minus 2. Again, I want to absorb it. So I have this number multiplying by with this operator acting on these. Now these all wi's, they go away. They all become identity.